So thank you very much for the invitation. I heard many good things about FFT from Alex Cloninger. This was joint work with Alex and with Dhruv, who is here in the audience. And this is supported oddly by the NIH. It is going to be used for neuroscience, so that's the connection there. So high dimensional data analysis, prevalent now across all fields. We are collecting data that has high dimensionality, many features, and the question is how to analyze such data. And an assumption that we can make is that while the data is represented using a very large number of features that we observe, it actually lies on some low dimensional manifold that we would like to recover. So we can perform dimensionality reduction and go from this point cloud in our high dimensional space to a low dimensional representation on which we can then do downstream analysis or explore our data, visualize our data. And the main focus of this talk is on data visualization. And then the question is how to reduce dimensionality, and a popular solution is taking the eigendecomposition of the graph Laplacian, and we've heard about the graph Laplacian in the previous two talks. And the conventional wisdom is that we use the top D eigenvectors of the graph Laplacian in spectral clustering and diffusion maps, Laplacian eigenmaps, and so on. And a question that we've been considering these past few years is this the best choice to take the top eigenvectors? I still have this animation. And a conclusion that we've come to is that you would actually like to look deeper into the spectrum, so not take only the first 4, 7, 10 eigenvectors, but there's a lot of information deeper into the spectrum. So I work joint with Xu Cheng doing this for clustering and segmentation of data. But today we're going to be talking about low distortion local eigenmaps for recovering manifolds and visualization of data. So what is a manifold? If we are here at UMD and we go outside, then we are on planet Earth, whose surface is a manifold. It is curved, but we look around and locally it is flat. We do not see the curvature of the Earth. Distances are Euclidean, walking to get coffee. But if we start zooming out and zooming out, then distances now need to respect the curvature of the Earth. We have geodesics. And when we want to now visualize the Earth in 2 dimensions and flatten it out into an atlas, then there are different distortions that we incur due to this flattening of the Earth. And this is what cartographers need to deal with, and they need to decide what kind of distortions they are creating by visualizing the Earth in 2 dimensions. And another problem that might occur is if you were only ever shown this map of the Earth and you didn't know what structure it arises from, then can you tell from this map, from our atlas, whether the Earth is a sphere or whether we live on flat Earth? So this is a problem with a lot of manifold learning techniques, is that we don't actually have an answer to this question once we visualize the data in lower dimensions. So gaps in existing manifold learning techniques. One problem that we'll show is that you only use a fixed set of global eigenvectors, these top eigenvectors, such as with Laplacian eigenmaps. And also your embeddings might not have low distortion everywhere. So if we take this very high aspect ratio rectangle and we try to embed it using UMAP and Mishne and Laplacian eigenmaps, and Dhruv, who is extremely meticulous, ran so many iterations of UMAP to try to get it to not have this twist, and it was practically impossible. So UMAP will always kind of twist this rectangle. Mishne, depending on the initialization, but using how they set up the original paper, breaks it up into these little pieces, and Laplacian eigenmaps, due to redundancy of the eigenvectors, will give us this parabola. And another problem, as I just mentioned, trying to understand whether we're living on a sphere or on flat Earth, is that if we take a sphere and we try to embed it in 2D using UMAP, Mishne, and Laplacian eigenmaps, what UMAP and Laplacian eigenmaps both do is they project the sphere along one of the directions of the sphere so that the top and bottom in the 2-dimensional space are now close to each other, and these points appear to be close to each other, though they are not. Mishne will actually tear the sphere apart and flatten it as we get with a map of the Earth, but the problem is that we now don't know that this originally was a sphere, and that points here are similar to points here. So I've mentioned the word distortion a few times. What do I mean when I say distortion? So distortion is a product of expansion and contraction, and it's the ratio and inverse ratio. We're taking the max distortion definition here of distances in your embedding space with respect to either your intrinsic or ambient space, depending on what we have access to. And the distortion is one if and only if our embedding, the distances are a scaled version of the original distances. So here, for example, if we take all our points and we just multiply the coordinates by 2, by the way. So we have no distortion, but however, in these two cases where we have some elliptical projection, then we're incurring higher and higher distortion. And what we would like are embeddings that don't distort our distances. Why? Because a lot of times we are trying to embed things that have physical properties. Distances between points matter, at least locally. And if you're distorting these distances, then this could lead to erroneous or artifacts in scientific conclusions based on these embeddings. So when we're embedding, for example, the unit square, one thing that we can think of is using two possible representations, cosine pi x pi y or cosine 5 pi x pi y. And for every point now, we're looking at very small circles, balls, and seeing how this representation distorts those balls. And we can see that for some locations, there is no distortion due to the pi x pi y, but in other cases, we get that the ball is distorted into an ellipse. And using 5 pi x 5 pi y, we get different locations in which these neighborhoods are distorted, which leads us to the idea that for different points on our manifold, we might want to consider different basis functions or different embeddings so that locally we don't have distortion. And the question is how to find these local representations of our balls on the manifold. So we present LDLE, which is low distortion local eigenmaps. And what we're going to do is we're going to choose locally or orthonormal eigenvectors of the graph Laplacian. So we're going to construct a global embedding from the graph Laplacian. We're going to take a large subset of these eigenvectors and then for different points, choose subsets of these eigenvectors. So each neighborhood is going to have its own parameterization. We're going to have these little puzzle pieces. And then we're going to do what we call bottom-up manifold learning. So we now have low distortion local eigenmaps, and we are going to align them together, put the puzzle pieces together in order to get a global embedding. And I'm going to show you how we find these local puzzle pieces and then how we align them together. Unfortunately, don't have presenter notes here, so I don't know how time is progressing. I'll try to stay on time because I know I am between you and lunch. So what our approach does is it also gives a solution that we can tear apart closed and non-orientable manifolds so that we embed them in their intrinsic dimension. What we'll see is that when we embed a sphere, we provide what we call gluing instructions. So we color the boundary of the manifold embedded into 2D so that you know that these points, despite the fact that they're over here, they actually also have neighbors over here, and the yellow points have neighbors over here. And we can imagine how to glue this together and understand, oh, originally this thing was a sphere. We don't live on flat Earth. And in embedding this high aspect ratio rectangular, so we don't incur this kind of twist or breaking apart that we saw with UMAP and Mishne. And furthermore, we're able to design LDLE so that if you know what your boundary is, if you know what points are out the boundary of your data, then we can take that information in order to obtain a better embedding of the data. So bottom-up manifold learning, in the first stage, what we want are low distortion local views, and this is building on a result from Jones, Maggioni, and Schul in 2008. And what you can see here in the plot, we are on the sphere, and there is this very local neighborhood of black points that is hopping around. And for every such local neighborhood, we're going to see its embedding in its selected coordinates. And what you need to look at are just the black points, and you can see that you get a very nice rectangular grid as we are hopping around, and every time it's different eigenvectors that are being selected, as we see here on the left and on the right. So we have different representations depending where we are on the sphere. How do we do this? This builds on, again, a theorem with the year change. Apparently this was 2008, but this is 2007. I think one is an archive paper, one is a PNAS paper. The theorem was that we have the existence of low distortion parameterizations of small metric balls on a Riemannian manifold using the global eigenfunctions of the Laplacian. But the parameterization itself is based on a subset of eigenfunctions of the Laplace-Beltrami operator. So for each such small metric ball, we are going to select a number of global eigenfunctions of the Laplacian such that embedding that ball with this local selection of eigenfunctions gives us low distortion. And what we did is we provided a discrete algorithm to realizing the continuous procedure that they proposed in the paper. And what they proposed is you take a subset of eigenfunctions S, and you start with choosing an arbitrary direction P1, and then you choose one of your eigenfunctions so that the inner product is sufficiently large, scaled by a factor that I'm going to skip, but you can see in the paper. And then you're going to choose subsequent eigenfunctions so that they are orthogonal to the gradients of the eigenfunction at that point. So this motivates the gradient of the chosen eigenfunctions to be locally orthogonal, and also that their magnitudes are similar. And the question is, how do we select these P's, and how do we estimate then the inner product in the discrete setting? So what we did is, again, looking, as I said, deeper into the spectrum, we decided 100 eigenvectors of the graph Laplacian that have a sufficiently large gradient at the point. And for P1, instead of choosing an arbitrary direction, we already have these eigenvectors that we've calculated. Let's choose one that is the smoothest and that has a large gradient at that point. And now what we need to estimate is the inner product between the gradients of two eigenvectors at the point. And again, we're going to choose them so that they are smooth. So we don't, if we have a number of eigenvectors that satisfy this condition, we want the smoothest ones amongst those. And the question is, how do we approximate this inner product of the gradients of our eigenvectors? So what we're doing is building on a result from Stefan Steinerberger and from Alex and Stefan, where they gave a procedure to calculate the local correlation between two eigenfunctions at a point. And what we have is that the limiting value of this local correlation, as they defined it, is actually the inner product between the eigenfunctions at that point. And we can take this continuous value and get a discrete approximation using, for example, finite sum approximation. And we also compared to other alternatives of calculating discrete versions of these inner products, and this gave us the best result. Again, the details are in the paper. And then we can move on. After we have selected the first eigenvector, we need to move on to selecting the second eigenvector so that its gradient is orthogonal to the gradient of the first one. This also relies on our operator AKIJ tilde. We'll skip this for the purpose of time so we can go on to how do we now align these together. But what we've obtained, for example, on the unit square, at every point, we now have a local representation to eigenvectors. And in the case on the left, we don't know what the boundary is, and we can see that there is higher distortion on the boundary compared to internally within the square. But if we do know what the boundary is, then we remove distortion along the boundary aside from the corners, which are still problematic. But we can, if we know what the boundary is, instead of just doing a regular graph Laplacian, we do what's called the double manifold, and we get the eigenvectors of those. So we can handle when we know what the boundary is, bring this into the manifold learning solution. And then this is an intermediate step. I'm going to go through it very quickly, but the idea now is we have for every point its local embedding, its local selection of eigenvectors. We want to align those. And that is very computationally intensive and also problematic, because how are we going to align this? We're going to align them where their local neighborhoods overlap. So for every point, we have what are its local neighbors, and we're only looking at every point individually. Those neighborhoods are rather small. So the neighborhoods are small, the number of points is huge. And what we want to do is cluster our neighborhoods locally into getting larger neighborhoods, what we call intermediate views, but so that they are still low distortion. So we're going to have a small number of intermediate views, which we can align. They have larger overlaps of neighborhoods, so solving the alignment problem is more stable and robust. And you can see still here in the middle, as we traverse and walk around on our sphere, clustering these views together still gives us representations or embeddings that have low distortion. So what we did in order to cluster the views, and this is a heuristic, we designed a cost for every point. We now want to cluster points together, and we cluster the points such that there is a cost that if you move a point into a cluster, it has to move into a cluster that is larger than the cluster it already belongs to, because we don't want points ping-ponging around. And we're moving it into a cluster for which, if we now embed this point using the embedding of that cluster, it has the lowest distortion among the possible clusters it can move into. So this favors moving points into clusters whose parameterization have the lowest distortion, and it favors moving points into larger clusters. So now that we have our intermediate view, we want to construct a global embedding, taking these puzzle pieces and putting them together. In our original paper published in JMLR, we had an iterative generalized Procrustes analysis. So here we can see kind of the iterations as the embedding improves. This is the embedding of a sphere. So these are the two caps of the sphere. And we can see again that we have these gluing instructions that tell us how to glue the sphere back together. What I'm going to talk about now is work that's ongoing. We're writing the manuscript, better options for doing the global embedding. So what we want is we now have these intermediate neighborhoods. Everybody's walking around with their own map of what their neighborhood looks like, and we want to put it together in order to get a map of the Earth. In the input, what we have are intermediate views. They're scrambled, they're scaled differently. They randomly somewhere in space, they don't necessarily correctly overlap with their neighborhoods. And what we want is a global embedding so that neighborhoods are aligned to each other. We're going to be using these locations where the points overlap between intermediate views. And you can see that there are going to be alignment errors. So the points aren't perfectly within each other. This pink point and this black point are the same point, but when we register and align them, that alignment isn't perfect. So our global alignment of local views, again, in the high dimensional ambient space. In the ambient space, the points are perfectly registered between these two neighborhoods. We have points that belong to two intermediate views. At the input, we now have these two intermediate views, and we want to bring them close to each other so that the overlapping points align to each other. So we can solve this optimization problem so that we have rigid transformation. We have an orthogonal transform of our points and a translation so that we are bringing all the points to the same coordinate system. And what we want is to do this so that we put a lot of effort into having low distortion in our local views and our intermediate views. We don't want to incur distortion in our global embedding. And what we did, we defined a global distortion, which is now the product of its expansion and contraction of path lengths. So we now have paths between every 2 points in the embedding in the ambient space. And again, taking the max distortion of this, we can show that if the distortion of the local views is bounded, so if you do this bottom-up manifold learning, you have low distortion of your local views, that distortion is bounded, then the global distortion of paths in the global embedding is also bounded by the squared value of the bound on your local distortion and your alignment error. And we can show from this that if none of your local views were distorted and you had no alignment error, then the global distortion was 1 and you're not distorting any of your paths in your global embedding. So in order to do global alignment of local views, again, Dhruv, being very meticulous, did a comparison of different techniques in order to do global embedding and solve this optimization problem. So a Procrustes analysis is what we call LDLE version 1. And while it solves the problem of fixing local misalignments in an iterative fashion, it's slow due to that. And what we found is that for LDLE version 2, Riemannian gradient descent is the best option. And we have at least sublinear convergence with appropriate initialization, and it is also the fastest, as we will see in a few slides, or on this slide. So we again have our input of our high aspect ratio rectangle, and when we compare Procrustes to Riemannian gradient descent, generalized power method, and to spectral alignment, Riemannian gradient descent has the least distortion, and it is also the fastest. It is the orange plot here on the left. So alignment error versus number of iterations or time, we can see that it converges the fastest to the smallest error. So I promised you guys that we can embed manifolds without boundary, and we can see here 2 examples, embedding the sphere and embedding a flat torus. And you can see for the flat torus that it perfectly aligns like puzzle pieces. If you were just to fold it on itself and fold it on the sides, then you would know that this is a torus. So a few results in 2 minutes, comparing a different geometry. So we have here a barbell where we have dimensionality of 2 on the balls, dimensionality of 1 in the middle. We also have both a square with missing data, holes, and a Swiss roll. You can't not give a manifold learning talk without having the Swiss roll with noise. We can see that LDLE preserves the geometry of the missing data, so we can distinguish between the circle and the diamond when we embed the square. None of the other methods do this well. We have our gluing instructions on the sphere, and we handle noise pretty well without getting distortion as Mishne does, and this bending that we see in the UMAP over and over again. Looking at a higher dimensional example here, what we have is a floor plan. Imagine you have 42 points in this floor plan that are, for example, Wi-Fi routers or hotspots, and now every point in your floor plan has the distances or a nonlinear function of the distances to these 42 points. So every point now is 42 dimensional, and we want to embed this and recover the geometry of the floor plan. And again, we're able to preserve pretty well the geometry of the holes in our floor plan. So if for some reason there was a column that was shaped like a lightning bolt or shaped like a triangle somewhere in the building, we'd be able to preserve that geometry. For manifolds without boundary, we have the curved torus and the flat torus, which I've already showed you. And in comparison, Mishne, as usual, tears things apart in weird ways. And UMAP and Laplacian eigenmap just squashes it along one of the dimensions. And we have this distortion that points on the top of the torus and the bottom are now close to each other in the 2-dimensional space. This is one of my favorite plots. Dhruv said, why not embed non-orientable manifolds? Can we embed the Mobius strip and the Klein bottles in 2 dimensions using LDLE? And what you can see very nicely here is that we can embed the Mobius strip as a 1-dimensional strip, tear it apart at the end, indicating that it needs to be glued back together. And we can also embed the Klein bottle from 4 dimensions into 2 dimensions. For this as well, we compared using different approaches to doing the global alignment. Again, Riemannian gradient descent had the fastest convergence and the lowest distortion and the lowest alignment error for all of these methods. Do I have time for a final example? Okay, so if you've ever seen Roy Letterman give a talk, he has these examples from alternating diffusion. He has 2 rotating dolls, a Yoda and a bulldog, and they rotate at different frequencies. And the embedding of this is a torus. If we try to embed this video, and you can imagine from UMAP and LTSA, okay, was this originally a torus or was this just some kind of ring? What we have from LDLE when we embed this is, again, we have gluing instructions so that you can see that this part of the rectangular embedding that we get should be glued to this part, and similarly here, and this maps back into a torus. So we know what three-dimensional shape this originally came from, and we're able to embed our rotating dolls into a dimension of 2, while preserving the information that the embedding should be a torus. So to conclude the talk, we propose a new manifold learning technique and general framework. So we have these modules that you can swap if you have some way to do a local embedding, if you have some way to globally align. You can get a low distortion embedding of your data. This is the older version of the code. Dhruv, what do you need to add to the GitHub link to get the new version, V2? Oh, it will redirect to the new version. If anybody is looking for a postdoc opportunity, I have a fully funded postdoc opportunity in my lab. Please contact me. Happy to talk over lunch or over email. And thank you for the invite. I've heard great things from Alex, and I'm really looking forward to the workshop.
Thank you, Don.